Thanks for the introduction. This is a recent work with Chris and Sam, and apparently they know it very well, so they're not here. Let me make some brief introduction on what we want to do in this work. So obviously, in my mind, that line defects, when we talk about defects in quantum field theory, line defects for me is the simplest object or simplest defect. If it's so simple, and then that means we have the potential to understand it quite well, and this is the line defect. The physical relevance for those line defects, probably you have heard it quite often, and there are quite few that I can name it. For instance, we can have, say, impurities on lattice model. We can also have Wilson line or loop lines. Those are probably in a more physical setup, but those will not be the topics for my talk today. And when we are talking about defect in quantum field theory, we can actually trigger a localized RG. And we know that when this RG, the localized RG, flows to an Wilson-Fisher fixed point, given the bulk is a critical theory, we can actually get a conformal defect. In this case, we have conformal line defect. And what does it mean to have a conformal line defect in this case? And actually, we can categorize it in terms of a symmetry perspective. And that means our theory, to start with, since the bulk is already at the critical point, it will, the global conformal group will actually be broken by the existence of the defect. And that gives us the orthogonal space, which is purely rotation. It's just purely made up of rotations, and then the residue conformal group underlying. And since this system is so simple, we would expect that analytical tools are still powerful enough to help us analyze the system through explicit calculations, analytical calculations. And the line defect is simplest in this case, and that in this setup, we actually can have a very simple bulk theory, which is just a free theory. That's probably the simplest of the simplest we can think of. And that will be my focus in this talk. So we will have a free bulk theory. An interesting question we can ask is that, given we have a free bulk theory, can we still have some interesting interacting theory on the line? That's the question we want to ask in this work. And there has been some answers that was given by the previous studies. Namely, there has been a work in 2020. There has been some systematical studies on the categorizing of defects given a free bulk theory by Loria. Liangdo, Van Ries, and Zhao. So in their studies, they give us an answer. They claim that the answer is no, we cannot get any interesting interacting line defect. Yes, please. Yeah, different people have different taste, of course. Here, by interesting, I mean it is interacting. It's not just the free theory, like the dynamics are not. In the bulk, you see, we have everything that is free, non-interacting. But can we still have some localized interactions? And that can give us some non-trivial correlations, which are not built by the GFFs. And by that, I mean interesting. Okay, thanks for the question. Feel free to interact at any point. So they told us it's no. And they were saying we only have trivial line defects. I will tell you what does trivial mean for them. It's really free. So the theory we are considering and I have in mind is a bulk theory that is just a free scalar without internal symmetry. This one. And they have some assumptions to arrive at this claim. The RG flow, you mean it ends on something? Yeah. We want a conformal line defect in this case. Okay. Okay. Yeah, maybe I got, you mean like a turn on a magnetization for the scalar field, for example? Right, so that can be a marginal theory. And so it's always at fixed point if we don't turn on any bulk interaction. Right. Right, the pinning fields. Yeah. Yeah, that's true in the epsilon. So if you have in mind that we turn on a pinning field defect, and in that case, in the free theory, indeed in the epsilon expansion, it doesn't land on anything. But once, because the beta function is basically proportional to this coupling. Yeah, I will show you. We can have some fermionic degrees of freedom, but those are basically quantum mechanics. If you wait for a while. They have the following three assumptions, or there are two that concerns us most. The first one is that they assume that the scalar equation of motion also varies at the correlation level. And of course, this is true classically when we are away from the defect we are thinking about. And the second assumption is time reversal symmetry is preserved in there, or time symmetry is a symmetry. Reversal symmetry is a symmetry in their consideration. And thirdly, they have, when we do the defect OP expansion for the bulk scalar field, and then there are many channels in the defect, and they assume that the identity, defect identity, is the only weight zero operator, such that this ensures cluster decomposition. Okay.
You assume that the equation of motion is valid also on the defect or not?
It is valid when we consider the bulk defect correlation, or any bulk, a bulk with any defect correlation at the correlation level is still valid. Actually, they still can have a solution to that equation, and actually this is not the old. I mean, this is just part of the equation of motion. Of course, there are delta sources to the line operators that can be explicitly depending on the model, and I will also talk about that later. Okay, and this we will actually also use, that the equation of motion is still valid, like it gives us 0 when the bulk insertion is away from the defect. And all right, maybe that answers the question. So this is still valid when bulk insertion is away from the defect. There's no coincidental singularities there. And we actually cast out. Do we have some? We actually have some doubts on whether these two assumptions are still necessary for a general study of the line defects. And it turns out those two can be invaded. But before talking about what we have been doing, I think I still need to explain what does triviality mean in their setup. So when they are analyzing the problem, they have a few observations to start with. The first one is that when we are applying this bulk equation of motion on the correlation between a bulk operator and a defect one, this actually, from this constraint, actually we can get the spectrum of operators that appears in the DOE of phi's on the line defect. And most interestingly or importantly, they analyze a bulk defect 3-point function, defect operator expansion. When they analyze such a correlation, a 3-point, the O hat, yeah, it's basically in the defect channels. Say this is Y orthogonal space. Or these are conformal blocks. And when they consider such a 3-point function by applying the equation of motion, what they found, so they can still, they use the spectrum of the phi field, and they found there are actually some non-physical singularities. So in this case, they actually put the operator, the second defect operator, at infinity. And they found that there are some non-physical correlations when phi is at the same height with one of the operator. So with O1, O2 is sent to infinity. And of course, we see that if the bulk is, if phi is a truly bulk operator, this cannot cause any singularities to happen if they are at the same time. And to kill this unphysical singularity, they get something called double twist condition. And this double twist condition basically sets an equation between the bulk channels, say delta L, and then this should be the two bulk operators, the two defect operators should have some fixed conformal dimension, like of this form, for example, where the twist is 2n here. This is called the double twist condition. And once we have this double twist condition, probably it's already quite clear to you that these are essentially giving us a relation, not a relation, but to give us a condition, to give us a result that the defect primaries appears in the phi operator, and the defect operators living on the line are basically generalized free fields. And based on that, since they are claiming everything here is just generalized free fields, and of course there are not any interesting dynamics that can happen locally on the line, so they claim that the theory is trivial. So in this sense, they are saying we only have trivial line defect in free bulk theory for the scalar case. So far, so good. Right. This is what they have done, and in our from the scalar. Yeah. So roughly speaking, the defect operators, once it satisfies such a relation, the spectrum of the defect OP are, roughly speaking, of the type like with transverse spin. So they're just integer dimensions, and they walk in a similar manner as generalized free field, or just free field, to weak contract with the others. Okay, so now I will tell you how to break these two assumptions, meaning to break time reversal symmetries, or this symmetry actually can be broken. And if you think about it physically, we have actually CPT invariance for field theory. So individually, this is not necessarily a symmetry of the theory itself. So in this sense, I mean, this can be broken. And secondly, we will find a counterexample that this identity is not just the only zero-dimension operator in an explicit construction. So the outline of my talk, or our result, will be as follows. So first, I will talk about I think in this case, the delta 0 is of bosonic type. The extra one.
You said you break it having only one.
Right.
Because if there's identity and then something else, the question is whether it's bosonic or fermionic.
The other is, in our construction, is actually also bosonic, is bifermionic. My outline today will be, first we will basically analyze again this bulk defect two-point function. And by analyzing this, we can actually get the defect spectrum of the spectrum of that appears in the in the defect OPE of the bulk scalar field. And the second step, we will consider the bulk defect three-point function by breaking this time reversal symmetry. And I will show explicitly a new cross ratio that can appear, that appears to break the inversion symmetry or time reversal symmetry in this simple case. And at the last step, I will actually construct an explicit toy model that satisfies what I'm talking about. So this will be localized Yukawa theory on the line, and we will introduce fermionic degrees of freedom along the line. Let me start with the two-point function consideration. Basically, we can make this bulk defect two-point function is fixed by conformal symmetries, and it has the form we consider a general defect operator with transspin L. And when I put the lower index, actually this means we are using the symmetric traceless representations of the transverse group. So basically, this means we are actually contracting the indices of this spinning operator with the null vector and this form can be fixed up to a data, which is the bulk to defect OPE coefficient. And in the denominator, it will actually have tell us about the transverse spin structure. And in the denominator, it will have the falling structure that is purely fixed by the conformal symmetry. And now if we put the equation of motion to be valid at the correlation level, we have a constraint by solving this equation. And this gives us the following condition for the spectrum of the defect operators. So it will tell us that it has two solutions. The first solution is that this defect operator will have the conformal weight equals to the conformal weight of the bulk scalar plus the transverse spin. Yet there is another solution, namely this operator has the conformal weight, which looks like the shadow do for the original defect operator. So those two are actually shadow duals along the line. As you can see, this gives us 1. So they are shadows of each other. And not necessarily. So when delta equals to 1 in 4 dimensions, that's the comment I will make. The spin 0 is actually has dimension 0. So this is allowed in the unitary theory. Thanks for the question. So in d equals to 4, we actually have the bulk scalar to be 1. And then for unitary theory, we should have this solution plus a solution that has 0 dimension. That's what we can learn from the bulk defect 2-point function by imposing the equation of motion. And now, let's move one step further to consider what they have considered for the 3-point function. But there is some difference. So basically, we can have 2 defect operators with different transverse spins. L2 and L3, and roughly speaking, we need to expand. We will get sum over the conformal blocks with different conformal weight as the intermediate channels. That's an interesting observation. So for this work, we are mainly concerned with a 4-dimensional case. But so far, the analysis works for a general dimension. Yeah. Maybe, yeah, it's interesting. Maybe I should think something more about 3-dimensional case. L is just an integer. It's the transverse spin. And the disconformal blocks for the bulk defect 3-point function will depend on a cross ratio. Normally, we can pick this cross ratio to be like the distances over each other. So this cross ratio, let's call it zeta, which are the distance between operator 1 and 2, and between 1 and 3. And then along the line, there is also a distance between the 2 defect operators, and lastly, the transverse distance of the bulk operator towards the line. And more explicitly, if we put this x1 to be y1, y1, y is the transverse coordinate, and the t is the coordinate along the line. In this case, more explicitly, we are actually considering the Lorentzian signature here. So if we'll have such form, and it's possible to show explicitly that this cross ratio is invariant under the conformal transformations. In addition to that, it's also invariant under inversion. meaning that we send x to all the coordinate here actually. And or equivalently in this special scenario or this special dimension for line defect, for the line defect especially, we have time reversal symmetry. The inversion symmetry is equivalent to the time reversal symmetry, meaning we send t to minus t. And this cross ratio, you see very easily that by sending time to the opposite, it will be invariant. And we want to say actually this cross ratio is not useful for our consideration. Let us take a further look at this cross ratio. It's more inspiring to look at the Euclidean case, and let's consider that. So basically, we just adopt the weak rotation and put a plus sign between the transverse direction and the time direction. And we can, in this case, we can actually explore the conformal symmetries such that we can put T1, T2, T3 at specific points on the frame. So let's pick a special case such that T2 is at 1 in time, but 0 in x, of course. So the line defect is along this line. And T2, T3, let's put it at -1. And then this cross ratio, we put also T1 at 0. So T1 is in the middle of T2 and T3 along the time direction. And in this case, we have simply this cross ratio is just dependent on the transverse distance. And you see clearly we can have a sphere that has T2 and the T3 as the antipodal points. And it's interesting that we can have two different insertions of the bulk point, say one outside this unit circle and one inside this unit circle. And the inversion tells us that y1 goes to 1 over y1. And then these two are basically related to each other by inversion. And this, in some sense, reveals the fact that this cross ratio is inversion invariant. And the problem it brought to us is that it cannot distinguish whether a point is outside this unit circle or inside this unit circle. So what can we do? We can actually, in this simple case, we can construct another cross ratio such that it can distinguish whether the bulk insertion is inside the unit circle or outside unit circle. And by the way, this circle basically causes the unphysical singularities for their construction, as this looks like an inversion symmetric point for along this circle. So basically, this cross ratio will be minimized, and the bulk will. No, that's not what I want to say. Anyway. Right. So we will actually construct another cross ratio for our consideration. Let me just take off my shirt. actually, we think that's if we cannot distinguish, this means that inversion symmetry is preserved. And in order to break this inversion symmetry in an equivalent way, means we should be able to distinguish what is inside and what is outside. So we actually used a new cross ratio, which we called nu e. Nu e squared plus 1 is actually psi e. And in this way, we pick a specific root for this equation, such that nu e will be tau 1, 2 times tau 1, 3 plus y1 squared over tau 2, 3 times y1. And if we still adopt this configuration by placing the operators in the associated positions, places, and we will have this to be y1 squared minus 1 over 2 y1. And you see now it can really tell us whether this point is inside the unit circle or outside the unit circle. And once we perform an inversion transformation, nu e will actually gain a minus sign. Such that it breaks the inversion symmetry. Or if you see from this expression, if we change the sign of the time direction, we will also get a minus sign, a total minus sign in front. You might wonder, does this still holds, this construction of this new cross ratio still holds in higher dimensions? Of course, we can still adopt some construction like that, but then you see this T12 and T13 will no longer just be a number, it's actually a vector. And that means we can have an extra angle between T12 and T13, and that can obstruct this smoothness across the unit circle. So in this sense, this cross ratio is very special for a line defect. All right, higher dimensional defect, exactly. And now with this cross ratio, we can consider the bulk defect 3-point function that we are interested and we want to analyze that part. You mean a codimensional 1 defect? Maybe in that case, we cannot really get a inversion breaking cross ratio. There are some underlying things here why we can construct such an inversion broken cross ratio exactly in this codimensional 3 case when the bulk is 4-dimensional. Actually, we can use, if we are going back to the embedding space, then we can use an epsilon tensor. Those runs in the defect directions in the 2-dimensional higher embedding space-time. And since now we have actually three insertions, so we will have say 3 points And this can saturate the indices for the epsilon tensor in the transverse, in the embedding spacetime. And because of that, this looks like a parity breaking expression in the embedding space, and when we translate it into the physical space, that corresponds to the inversion symmetry. And if we have a codimensional one case, maybe in general, these indices cannot be saturated in such a way. And I tend not to think that this can be constructed. Or do you have something in mind? Okay. Right. So now let's going back to our bulk defect 3-point function. First, we will make an ansatz on the conformal blocks. And you see, here we have actually, okay, I will write it again. We have two defect operators with two different transverse spin. And we need to take care of the representations here. And in order to do that, we have the following ansatz. So basically, there are L2 P2s that is contracted with this tensor, and L3 P3s. So P2 and P3 are the null vectors that this is contracted with this tensor. And we need to make the degrees to be the same on the two sides. And we pick this choice, so without loss of generality, we take L2 to be larger than L3. And then we can have the normal vector N1 that can be dotted with P2. And then we have also P2 and P3. You mean when they are two? Yeah, that can happen. Thanks. And you see, now P2 has power L2, and the P3 has power L3. And that means the new thing there should be a degree 0 for P2 and P3. And why? Sorry. This is the transverse vector, the unit transverse vector. And there are also some structures comes from the conformal path, which are the distances to L2, x1 to delta 3, and then y1 delta minus delta 2 minus delta 3. And then we will have a sum over the conformal blocks labeled by the spinning channel for the bulk operator. And we assume there is a coefficient that we don't know, and then a conformal block that is dependent on the cross ratio we have constructed, and then a new structure coming from the representations of the transverse group. It will be covered inside this chi. So chi is defined as a kind of new cross ratio that is taking care of the transverse spin part. And as Giuseppe was pointing out, why we cannot have the other structures, and it appears to be here. since we want a degree 0 in P2 and P3, so this will be constructed as follow. And L2 and L3 labels the traceless symmetric representations of the transverse group SOD. In this case, actually, we can have L. So this L is not arbitrary. It actually should be within this range, starting from L2 minus L3, and the jump every second on this transverse spin until they reach L2 minus L3. This jump of 2 is because we need to contract a pair of indices to reduce the spins. And we expect somehow, if we apply the equation of motion on this conformal block, we should get something that corresponds to the conformal group SOD minus 1 and SO 1, 2. And those should be somehow the Casimir's should appear in this equation after we put in this constraint. And we expect there should be some part that is an eigenfunction, has the eigenvalues of this L plus D minus 3 times L. And for the residue conformal group, we should have some Casimir looks like delta L times delta L minus 1. Those are just expectations at the moment, and indeed, those are found while we really apply the equation of motion on these conformal blocks. Since I have talked about such a kind of structure with epsilon tensor, you might wonder, can it also play a role in this construction? Actually, it does. That is also a special case of 4-dimensional theory when the full bulk space-time is 4-dimensional. So in that case, we can have another structure built by the epsilon tensor. This is a special case for Dukes to 4. And we have 3 indices in the transverse group. And the structure we can have is very similar to what we have there, but now there is an addition structure built up by epsilon tensor. I will just write it for completeness, but actually during this analysis later, I will not really use this part. And then the conformal structures, and as well the conformal blocks. So the L's here actually runs differently now. The L's here will run only the things that has been jumped from that part. So namely, this L will run from L2 plus L3 minus 1, and then decreasing 2 at each time till L2 minus L3 plus 1. Interestingly, that this function here that controls the conformal block remains the same for both, for this structure, this parity broken structure, and the other one. The difference will be the H tilde part that comes from the transverse group. Yes. It's true for any spins in 4 dimensions. you see here, it also has degrees. But the power of P2 is, sorry. That's my mistake. It's basically the same, except this epsilon tensor. And this will not play a role. But maybe this is also interesting to be analyzed further. Oh, okay, no. So this F will remain the same. So it depends on L and the cross ratio, and independent on the values of L in which set, the equation for FL will remain the same. The only difference is the HL part that comes from the transverse spin, or the representations of the transverse spin. The parity breaking in the context we are talking about, no. Though I believe it's still a kind of parity breaking term. And to put a constraint, we acted the Laplacian on the bulk defect 3-point function. And this is only one equation, but actually from this expression, it can be separated into two equations, and each part satisfies an equation separately. So namely, this one equation can be decomposed into two equations, one for FL, and one for HL. There is some huge simplifications in this consideration, but the result looks very simple. So the resulting equation has such a form. It is a second order differential equation, as you expect. And in this equation, we see the Casimir structure that we expect from the SO1, 2 part. That is the eigenvalue. So f of L is an eigenfunction. And the second equation, this delta plus minus equals to delta 2 plus minus delta 3. And there is a second equation that deals with the H part. Let's focus just on this parity even case and neglect this structure. And this tells us that we have an equation which is 1 minus 2 chi The form is not so inspiring. I have to apologize that. And then there's another part. And this part shows up. Okay, very nice. So basically, our goal is really to solve those two equations and then get the allowed structures. Before solving the equation 1, let's take a look at equation 2. And as it is a second order differential equation, it will have two solutions. But if we put this boundary condition that when chi is around 0, this should, when we expand this function around chi equals to 0, it should behave as 1 plus something else. This is because we have already put the highermost structure for P2 here. And then this will select the solution that we want. It has it is a hypergeometric function, which is not so inspiring. So I will not write it here. But this boundary condition is necessary for picking such a solution. And there's another way to get the form of H of L by purely analyzing the polynomial representations of the transverse group. The idea is really to pick the scalar representations after tensoring the spin L representation and the spin L2, spin L3 representations, and we want the kind of scalar representations with a spin 0, such that the one-point function of that will not vanish. So that's an alternative way we can obtain the form of HL. They are. Yeah. Yeah. That's what's happening, exactly.
You're saying you get some constraint from the fact that you know it should be a polynomial when you sum?
Yes. You mean it's not an infinite sum? Yeah, yeah. What is this constraint? The constraint, I think, is really from here. We have the two defect operators. First, we tensor them. And now we know the allowed channels for this tensoring. And then now we need to tensor with the defect channel phi. And the total spin should be 0, such that that is not vanishing at the correlation level. So that is the constraint we need for getting the polynomial representations in such a way. I can tell you the details maybe later. It's actually, we did it in our appendix. Now we can take a look at equation 1. It's actually also a second order differential equation. And you can expect there are two independent solutions. And in the new coordinate, this has very simple form. The f of nu will be nu squared minus 1 to the power delta 2 plus delta 3 over 2. And then the two solutions will be given by the associated Legendre function of p-type and q-type. Those are the two different solutions for this equation for this equation for f of L. So why a physical understanding of why we have two solutions for this equation of motion is that they are, so basically we have two conformal blocks, and one is the shadow blocks of the other. And at this stage, we cannot get rid of the shadow block. And that's the first comment. We have shadow blocks. The second comment is, as you see, this conformal block is actually regular around nu equals to 0. And this is the Euclidean picture, but we still have want regularity around nu equals to 0. So nu e equals to 0 in the Euclidean picture corresponds to the unit circle. And we want it to be regular there. And their main concern is that the regularity around the unit circle gives double twist condition. But in our construction, you see, we don't run into this issue of unphysical singularity around nu equals to 0. It's completely regular there. But now if we want to consider the short distance behavior, such as when we move the bulk operator towards the defect, or to put these two defects towards each other, there are some short distance leading behavior in the OPE regime. And for that, it's more inspiring to go back to this theta coordinate. So if we go back to this theta coordinate, and we will also get two branches of solutions. And let me write it down, because in here actually we can pick up the correct solution, which has the nice scaling behavior when we take the two limits. So it will have the first branch, which let's call it C prime, and that has that theta it's set up to the power delta plus L minus 1 over 2, and then a hypergeometric function. And there's another branch, which is also a hypergeometric function. And now we can take the limit when the bulk operator is approaching the boundary. And we see when we take this first limit, y1 goes to 0, the two solutions will behave differently as a power of the short distance. So C1 prime will behave as y1 to the power delta minus delta L plus 1. And C2 will behave, the C2 dependent part will behave as the desired one, which has this correct short distance behavior from the bulk primary. So in this case, we actually should pick the C2 solution as the one that has the correct boundary behavior. As a consistent check, we can also take the limit when the other OP limit when the two defect operators are approaching each other. And in this case, we will have the following leading short distance behavior minus delta plus minus delta L plus 1, and then again the C2 will pick the correct scaling. A comment here is that if you look at this C2 dependent solution, if we really impose the double twist condition, that means one of the entries in this hypergeometric function will become a negative integer if we impose the double twist boundary condition, double twist condition, and that means this will terminate at some order. It will actually become a polynomial in 1 over zeta or in zeta. And again, we will not see any singularity around nu equals to 0 or zeta equals to minus 1. But as I have showed you using the new coordinate, a new cross ratio, that we will the conformal block will actually be regular around 0. So no need for the double twist condition. That is actually central to their proof. So here we don't really need double twist condition, or in another word, this double is not. It's okay. So they find some unphysical singularities around this circle in Euclidean signature. So this circle corresponds to nu goes to 0, and eta equals to 1 in the Euclidean case actually. And they say, because you see this has no colliding limit, so there shouldn't be any physical singularity around the circle. And in order to kill this singularity, they find this double twist condition such that there's no branch guard, blah, blah, things.
When you're saying that doesn't need to be imposed.
That doesn't need to be imposed, as we don't see any unphysical singularity in while we solve the equation of motion using the new cross ratio, which breaks the parity invariance. The P's and Q's are the associated Legendre functions. They are regular from at 0. Okay, I guess I can still have time to talk about the last part, which is an explicit construction. This is 2. Okay. So now we can construct a model explicitly. In this case, it's actually a localized Yukawa interaction. In addition to the free bulk action, we can introduce an action on the line, which is dynamical for the fermion. and it interacts with the bulk through the Yukawa coupling term. And in order to give a proper boundary condition for the bulk scalar phi, we introduce also a pinning type of defect. And now I want to show that this model explicitly breaks the two assumptions that they have in their work. So the first one is the time reversal symmetry. Which act on the fermions as following. So psi goes to psi bar, and the psi bar goes to psi. This is a complex fermion, and it is anti-unitary, meaning we will send I to minus I. And then you see the kinetic term actually preserves the time reversal symmetry. However, this interaction, the Yukawa term, will break the time reversal symmetry explicitly. So once we perform the time reversal symmetric transformation on this Yukawa term, what we will obtain is phi psi bar, and this is such that the time reversal symmetry is broken in this model. And the second thing is the dimension 0 operator along the line defect. We can take an advantage of the equation of motion of the bulk, the full equation of motion. So we need to consider the delta sourced term along the line. Actually, this operator is protected by the equation of motion. And through dimensional analysis, in exact d equals to 4 dimension, we can see this operator has dimension 0. This is because this is d minus 1, and this has 2, and the other has 1. So 3 on left side and 3 on this side when d equals to 4. And exactly this will be a dimension 0 operator. And now the question is, does this model, although now we have an explicit model that breaks their assumptions explicitly, will, of course, the triviality in their sense doesn't hold in this case anymore. However, is this model still trivial? This looks very trivial. It's a very simple model. And the triviality of this model can be shown via a field redefinition. So this is an interacting model we have via Yukawa interaction. Actually, this Yukawa coupling can be absorbed into a new field through field redefinition. And this field redefinition works as following. So we can basically get a new field, say psi bar, and absorb this interacting term into the exponential part. And then you see when we take in the derivatives on t, this will cancel the Yukawa term such that it will become a free theory. And of course, on the psi part, we will have the minus 1. So this field redefinition actually transforms this interacting theory to be a kind of free theory for fermions. the fermion and the boson will be decoupled from each other in the new primed action. So because of this field redefinition, the physics is the following. Initially, we have an interacting theory along the line, and the fermions are interacting with the bulk field through this Yukawa interaction. And now, through this field theory redefinition, we are going to a kind of free fermionic theory plus a bulk theory with a pinning type of defect, which gives the boundary condition for this bulk scalar field. And it looks, now we have decoupled two theories. Actually, both of them are free in some sense. You might think, oh, this theory is so trivial, so we don't have any useful information, but actually it's not true. The thing here is that through this field redefinition, although in the psi part, those looks like free theory, but for the psi prime part, those looks like free fermion. But actually the correlation between psi and psi bar will not be that of a free fermion. It's because this vertex operator are actually contributing. And this gives an anomalous dimension for the fermions along the line. And we can calculate explicitly. Mm.
Really, the theory is fermions like some flux attached or something. Because time reversal should still be broken.
Yeah.
How do I see that after?
That's a good question. That's a good point. Maybe. So this, if we consider still time reversal symmetry on psi, actually seems like psi will go to psi bar. But it's not the same because this will get an extra minus. And the psi goes to psi bar. You mean this? I also get a minus. Right. That's a good point. Maybe it's not so easy to see it explicitly.
It looks like free fermions, but time reversal is still broken, and you have anomalous stretch.
Mm-hmm.
In your paper, you mentioned that field redefinition is non-local.
Yeah, this is because it's an integrated. Right. So basically, we can still calculate the two-point function using this field redefinition. What we need, adjust the free Green's function so that phi is at d equals to 4, it's x 1/2 squared times 1, sum 4 pi, 1 over 4 pi squared. And then the fermion actually will be a Heaviside zeta function. This is because we can treat this one as the psi bar as the creation operator and psi as the annihilation operator. So the order has to satisfy in order this has non-vanishing correlation. And then we basically use this field redefinition, and then we can get psi bar. So it will now look like t minus t prime with the scaling dimension minus 2 delta psi, and delta psi will be minus g squared, plus g squared over 8 pi squared. The same goes for psi bar. And due to this field redefinition, basically we can calculate all correlation functions in this theory exactly. So in this sense, it's still somehow trivial model, but not in the same sense as what they are considering. So this is the main message, but you might wonder, we have done some general analysis and we have a model. If we consider some 3-point function, do they match with each other? And the answer is yes. To see it explicitly, we can simply consider this model. This correlation. We can consider phi with psi. And this one will give us some g squared over 8 pi squared ig actually. And then with the correct structure that we can obtain from the associated Legendre functions, it will have this hyperbolic tangent, arctangent, and then the conformal part. So if you look carefully at these Q's and the P's, you will find that only L equals to 0, the spin 0 part will contribute. This is expected as those are spinless operator with spin 0 with 0 transverse spin. So at 4 dimensions, this becomes marginal. So any h is exact marginal. We also did some, okay, so both g and h are exactly marginal in 4 dimension. And we, before knowing how to do this field redefinition, we actually did some Feynman diagrams calculation on the g part, and we found this up to order 4. There's no corrections. The beta function vanishes. And in this case, only the spin 0 part will contribute. And then we will see that Q0 is the hyperbolic tangent. But this is 1 over nu. So actually, we also need P0 part to kill some I pi's, the imaginary part. And indeed, through an admixture of Q0 and P0, this correlation function of the localized Yukawa model will match with the general analysis we have before. We can also consider some more complicated 3-point functions, and among those we have considered, they always match. We also considered higher transverse spin defect operators by putting a spin on the phi's. It's basically derivative of transverse derivative on phi's with psi's. They form a conjugate, a composite operator, and they also satisfy this relation we did for the general analysis. And the last interesting thing is, actually, you might wonder, normally when we talk about the defect, we can also analyze the localized RG flow through the so-called G function. And in this case, actually the G function vanishes. This is because of the field redefinition. So once we perform the path integral, we calculate the partition function on this sphere, and performing this field redefinition, the measure for the fermion part actually got cancelled, even though we have even though we have this field redefinition. And then we can show the G function vanishes at 4 dimension. It's actually reasonable because basically it's those two couplings are exactly marginal, so we don't really have any RG flow along the line. And then maybe the RG properties proved by the G function is not so influential. But that's just a consistency way of seeing things. But we did the calculation exactly, so we think the G function vanishes. Exactly. In the end, it becomes a decoupled system, although there's still interaction. It's kind of, yeah, it's hard to put a borderline between this interacting and free. Oh yeah. Right, so that appears here. And you can check explicitly. So H is just a number, a coupling times the identity. And then you can check also through the field redefinition, psi bar psi as a composite operator has 0 dimension. It cancels with each other, so then that's